Hello. Uh, we learned that you may use one of these three models, and I will compare how they differ in their interpretations. And actually, we already used this model in an earlier slide. So we studied the effect of student-to-teacher ratio on test scores using the dummy variable. So by dividing the data into two different groups. So, and at that time, the conclusion was that the regression is actually no different from calculating the difference between two groups' averages, two groups' average test scores. So we are going to use that approach again, and because that will tell you better picture what we are doing here. So first, consider the first model where the test score is regressed on the intercept and the small variable. And remember, we have two groups, small or large, and I'm going to calculate, say, in the data, some school districts are included in the small group, and the others belong to the large group. So, and calculate the average test score for each of those groups. So first, if you calculate the average of test scores from the small class size group, then according to the model, it's small class size, so they have small equals to 1. Every school district that belongs to this, that satisfies this condition will have small equals to 1. So beta 0 plus beta 1 times 1. Small equals to 1. So this is the conditional expectation given this condition. So beta 0 plus beta 1. But if you consider the other group, in the large class size group, the small takes 0. So this variable equals to 0. So replace small with 0. Then beta 1 will disappear. And simply the conditional expectation is beta 1. This is exactly the definition and the interpretation of beta 0, the intercept. Beta 0. The intercept is the expected value of the outcome variable when the regressor takes 0. So that's beta 0. That's the intercept. That's the average test score for the large class size group. Then it is clear you have two averages calculated from the data, small class group, large class group, and their averages. And you have two parameters, beta 0 and beta 1, but the relationship between two averages and two parameters is given by this. And it is easy to see that beta 0 can be interpreted as exactly what I said, the average test score for the large class size group, and beta 1 is the difference between these two groups, right? So small class size group has higher test score on average by beta 1. So that's the difference between these two groups. This is what we learned earlier, and we are basically reviewing the result. And what's interesting here is I'm going to change the regression model from using small to using large. So you dropped the other variable. Now we consider basically the same model, but using different definition of the dummy variable. In this case, I'm going to do the same thing, but what is interesting here is previously the former was the small class group had beta 0 plus beta 1, and large class group had beta 0 plus beta 0. But find that the large variable, this dummy variable, takes 0 and 1 in this way. Small group has 0, large group has 1, right? That's the definition. So beta 1 survives only in this group. So the beta 1 is relevant only to the large class size group. So the interpretation of those parameters must be now different. Beta 0 is the intercept, which is the expected test score when the regressor takes 0, right? And that represents the small class size group now. Previously, beta 0 was for the large group, but now by changing the variable, the regressor you use, beta 0 is now capturing the other group's average. So, of course, if you estimate if you look at the estimation results, it'll be different, and interpretation must be different. And beta 1 is, as before, is the difference between these two groups, the difference in the averages between these groups. But the order is now different. What you subtract what from what. Now you subtract small from large, which is the opposite of the previous one. In the earlier model, beta 1 is defined as difference between these two, but you subtract large from small. But now, small from large. So it is. So in the end, if you recalculate everything, then they must be consistent with each other. However, the interpretation must be different. So you have to. It's easy to understand what's going on here. And the last model is to drop the intercept. We drop intercept, and I will use beta 0 for small and beta 1 for large. Maybe this is the first model you don't have the intercept. In this case, let's calculate the average by group, and then if you have small, then small equals to 1, large equals to 0. So 1, 0, and large group has 0, 1. So it's like encoding. So the small group only has beta 0, excuse me. Small group's average is simply beta 0, and large group's average is simply beta 1. So it is easier to interpret what they capture, but again, it is different from any of the earlier models. So as you can see, so what I said so far was that multicollinearity is a problem. You cannot use all the multicollinear regressors at the same time. So, but the solution is simple. You have to drop one. But it is your choice which one you drop. So you may drop the intercept, you may drop x1, you may drop x2. But the problem there is, so it does not matter what you drop, but what matters is how you interpret the model. So depending on the model you use, you have to interpret those parameters correctly based on the setup. So, and there is no best one, but as you can see, they are capturing different things. If you are interested in the effect, the difference itself, then I would use this or this. But if you're not interested in the difference but their absolute test scores, then this would be better, right? And if you compare these two, I think this beta 1 will be positive, and it was positive in our empirical example. So I would prefer use this one to using this one, because if you use this model, your parameter estimate will be a negative number, which is a little more cumbersome to interpret and to present and to explain. So everything should be converted to the negative side or positive side. So so it is only for convenience. Nothing is wrong as long as you interpret correctly. So, and final intuition here I would like to give you here is that you have two groups, so you can calculate two averages. So in the regression model, you can have only up to two parameters. More than two parameters, something is wrong. You don't have three groups, so you only have two averages. So from two averages, you cannot estimate three parameters. That is the simplest intuition, underlying intuition in this case so far. And the same intuition holds even when the model becomes more complicated. Like for example, if the dummy variable has more than two groups, like three groups like this, rural, suburban, urban, suppose that they are exhaustive, so you have to choose one of the three. And as before, you cannot include all these dummy variables at the same time, as well as the intercept. It is not possible. So intercept, rural, suburban, and urban, it is not possible. Four variables together have a multicollinearity problem. And intuition is the same. If you use this model, this model has beta 0, beta 0, beta 1, beta 2, beta 3. There are four parameters. So, but you only have three groups in your data: rural, suburban, urban. So, three groups cannot estimate four parameters. That is the simplest way to detect this problem. And as the solution, you have to drop one of them. Any of them, it's up to you again. And you may drop the intercept, or you may drop one of the category, one of the groups. But as before, the interpretation should be consistent with your model. And how you interpret, you think about this case. Now you will have three averages by group, and three parameters to be interpreted. So depending on your model, think about which parameter is capturing which group, and also so how you interpret those parameters. Okay, so that's I will stop the video here, and I will continue more discussion about multicollinearity in the next one. Thanks.